All right, now we're recording. So I guess I have to do some DE now. Okay. It is possible that we might end a semester early if it turns out that everything can be covered. I'm still trying to figure out exactly how far I need to get. I know I'm supposed to get into chapter 6, but not necessarily the whole thing. In any case, I plan to be starting at chapter on Wednesday, depending on how far we get today. Okay. All right, so I still have a little bit of mop up from everybody. Got the secret of analysis? That should not be a secret. Well, those 4 of you who need it. Okay. Whoa. Oh, the chalk broke into 3 pieces. That makes me like 42% of a Jedi.
I was going to say, that's supposed to mean something.
Yeah. Part way, yeah. So I need to work on my technique a little more, apparently. Okay. Sorry.
It'll cost you an arm and leg.
Should be somewhere more accessible.
Okay.
Yeah.
Oh, but now it's hidden.
Yeah.
Okay.
Totally against recycling, huh?
So, at the very end of class on Wednesday, long enough for you to forget, I stated this proposition about relating systems from Cartesian to spherical coordinates. Okay, so this system with functions a, b, and c that depend only on the distance of a point from the origin. Is equivalent to this much simpler system in spherical coordinates. Rho prime is a of rho. Theta prime is just b of rho. And p prime is c of rho sine phi. Okay, so I want to look at a couple examples of these. So first example, we'll let a equal 1 minus rho, b equals 0, and c equals 1. So if you, so what that means is this system, which is 1 minus rho x plus xz, y prime is 1 minus rho y plus yz, and z prime is equal to 1 minus rho z minus x squared plus y squared. So that system is now equivalent to rho prime equals 1 minus rho. Theta prime is 0, so theta is just going to stay constant. So we're going to stay in one plane. Theta equals constant, only rho and phi are allowed to vary. And phi prime is equal to rho sine phi. Okay. So now we can understand the behavior of the original system by studying the behavior of this much simplified system. For one thing, we can look at fixed points. Okay, so you want to look at values of rho, theta, and phi that will cause all 3 all three equations to be 0. Now theta could be anything, doesn't matter. So what would be values of rho that would make this a fixed point?
0.
Yeah, so rho equals 0. Now n1. Let's look at rho equals 0. So that's 0, already 0. And then that'll be 0. So, but the thing is, rho equals 0, what point is that? It's just the origin. So rho equals 0, and then phi can be anything. So just the origin is a fixed point. Not a very interesting one. Now, the other fixed point, theta, can again be anything. But it's going to be a fixed value because it's going to be a constant. Rho equals 1. And then what has to happen with phi in order to again make this a fixed point? Keep in mind, phi has to be between 0 and pi. Those are the allowed values for phi.
So 0 and pi.
0 and pi.
0 or.
Yeah, phi could be 0 or pi to make sine phi equals 0.
Oh.
Yeah. Okay. All right, so really we have, so we confine ourselves to just one plane, theta equals constant. Within that plane, we just have basically three fixed points. The origin, because let's look at these in basically rho phi space. So we have the origin, so that's rho equals 0. And then rho equals 1, phi equals 0. What point is that? Because phi is the angle of inclination against the positive z-axis. This is the angle phi. So if phi is 0, we're up here. It's basically like the North Pole. So the top of the unit sphere, rho equals 1, phi equals 0. So that, in other words, that's the point 0, 0, 1 in Cartesian coordinates. So where's the other fixed point?
Opposite end.
Yeah, down here. So this is where phi, rho is again 1, phi equals pi. So this is a point 0, 0, minus 1. Okay. So now the question becomes, if you have a solution that's at any other point in spherical space, away from these fixed points, is it going to approach any of these fixed points? Okay. So, all right. So what's happening is, I'll repeat the equations over here. Or at least the interesting ones. All right. Now, for rho, here are the intervals of interest. We have, well, we don't care about negative rho. And we care about rho between 0 and 1, and also rho greater than 1. So, if rho is between 0 and 1, what can be said about phi prime? It's not 0. Is it positive or negative?
No.
What?
Like rho between 0 and 1?
Yeah, rho is between 0 and 1. So we plug a positive value between 0 and 1 in for rho. Is this whole expression going to be positive or negative?
Phi prime, right?
What?
Phi prime?
Positive, beta prime?
I can't.
I said positive.
Yeah, okay. Sorry, I didn't. My hearing sucks. So, yeah, it's positive. All right.
Rho prime.
Oh, rho prime.
Yeah, so if we look at like a phase diagram, so this is our phi axis, and this is, actually this is our rho prime axis. Yeah. So the way the solution's behaving, if rho is between here and here, it's going to be, here's our fixed point, it's going to be increasing towards that. So it's tending towards this fixed point, not to one down here at rho equals 0. Okay, what happens when rho is greater than 1?
Negative.
Yeah. So again, it's tending towards rho equals 1. So either way, so solutions that are away from rho equals 1 in either sense are still approaching rho equals 1. So what this is saying is all solution curves approach the unit sphere. But what we don't know is where on a unit sphere. Now, we are confined to a single plane in terms of theta. Theta equals constant. It can be any constant. So if theta equals constant, then what's happening is in three-dimensional space, so we have some plane, theta equals constant, and rho is equal to 1 within this plane, we have this circle. So all we know at this point is solutions are converging to something on this circle where rho equals 1. So it's like a slice, a cross-section of the unit sphere. But maybe we can narrow it down further, because we also have to look at phi prime. So what's happening is, if phi is between 0 and pi, then and rho equals 1, what can be said about phi prime? Is it going to be positive or negative?
Positive.
It's going to be positive because sine phi, we're between 0 and pi. That's quadrant 1 or 2. Sine is positive on those quadrants. So phi prime is positive. So that means that phi is approaching the upper limit, pi. Bless you.
Excuse me.
So what's happening here is, if I were to draw a similar diagram for phi, I'll be approaching that upper limit phi equals pi. So if rho is approaching 1, phi is approaching pi, and all solutions converge to what point?
0, 0, -1.
0, 0, -1. So everything is being driven down here to this point. Okay, so that's the key behavior to observe here. But the thing is, solutions start at whatever plane theta equals constant. The solutions have to stay within this plane. So wherever they start, like it's out here somewhere, or out over here, wherever they are, they're going to be drawn to this, and they'll stay there. So it just keeps converging to that as t goes to infinity. All right. So if you were to plot solution curves with different initial values, you would see this convergence, but you would notice that the convergence always stayed within this one theta plane. Now, if you chose a different theta, going through in this direction, you'd still see its convergence to this point, but it stayed within that plane. Okay, so that's one example. Now, so now that we see how the solutions are behaving, suppose I change the example a little bit. What if my function here and what my function b here, which is 0 before, what if b was equal to 1? So in that case, if I look at this proposition here, the equations for rho prime and phi prime are not going to change. However, this equation will. So I have a new equation, theta prime is equal to 1. So what happens for the fixed points? So the fixed points we found over there. Like, because now we have this new system of if rho prime is 1 minus rho times rho, and then phi prime is still rho sine phi. So what can be said about fixed points of this system?
It would be the same, except theta would be 1.
0, 1, 1, 0, 1, negative 1.
Well, what does it mean to be a fixed point?
So they
All
all have to be 0.
have to be 0.
Oh, yeah.
No fixed
no
points.
Fixed point, yeah.
Now, we've talked about the situation before, where, because first you can look at fixed points, and then after you've finished discussing fixed points where all of the equations are 0, then you can look at cases where 2 of the 3 equations are 0 and 1 is not. So instead, we have invariant lines. So 2 of 3 equations are 0. So where can we find invariant lines? So the theta equation, that's hopeless. That's never going to be 0. But what about the other 2?
Rho equals 0.
And?
Rho equals 1.
And?
Phi is 0 and pi.
Yeah, in other words, the points that were fixed points before are now invariant lines. Okay. But the thing is, so we have, so rho equals 0, rho equals, that's one fixed point, here was rho equals 1, and phi equals 0 or pi. But here's the thing. Where are these points? If the origin, the North Pole, and the South Pole. At those 3 points, and only those 3 points, the value of theta doesn't matter. So, so we still have a point 0, 0, 0, 0, 0, 1, and 0, 0, minus 1, regardless of theta. So here's the thing. It sounds like there are fixed points, but this says they're not. Why is that? That's not a contradiction because these are in Cartesian coordinates.
Sweet.
When I say no fixed points, I mean in spherical coordinates. Ultimately, we go back to what's happening in physical or Cartesian space. So, because really what's happening here is, these are unique points in Cartesian coordinates, but in spherical coordinates, these are described by infinitely many points. Like you take these values of rho and phi, Cartesian product with all possible values of theta, from minus infinity to infinity. So you have to think about what space are you really in, what coordinates are we talking about. An invariant line in spherical coordinates could be something completely different. In fact, almost will certainly be something completely different in Cartesian coordinates. In this case, in Cartesian coordinates, we still have a fixed point. So if you were to do the same kind of analysis with what happens to rho prime, what happens to phi prime, you would find the same thing, that solutions still converge to a point at the bottom, 0, 0, minus 1. However, the fact that theta prime is now equal to 1 rather than 0, it does not affect the final result. They still converge to that point. But it does have an effect, because if theta prime is equal to 1, what is theta?
T.
Yeah, it's going to be t plus a constant.
What's the
Yeah. Okay. So what's happening is you have a point that's somewhere up here at the start, at t equals 0. Then you know it's going to wind up down here. So in terms of rho and phi, it will, rho will approach this unit sphere, phi will approach pi, and send you down here. But because theta is now equal to t, what kind of convergence, like visually, are we going to see?
It will be elevated by t? I don't know.
Well, think about what theta means. The angle theta in spherical coordinates. So what is it? So in the first scenario where b is 0, it stayed within this theta plane and just went straight down here. What's going to happen this time?
So is it going to like follow the circle?
What circle?
Unit circle?
Oh, this? No, because this circle is confined to a plane theta equals constant. Theta is now an increasing function.
So it'll be circles.
Spiral?
Circling out.
Yes, it's going to spiral around the z-axis on its journey to the South Pole. Yeah, so you can see like a helix effect in a way, because it keeps spiraling around the z-axis. Yeah, so it's interesting how a behavior can change just from a slight change to the system. Even though the end result is still the same, visually at least the behavior is a lot more interesting. Okay. So this is why we do these transformations, like for example to polar or spherical coordinates, because try figuring it out from the original system. That is so not happening. But at least by getting a much simpler system in spherical coordinates, and where we can study the behavior one variable at a time, and we can see whether solutions are being drawn to certain fixed points, or invariant lines in some sense. That way we can see how the solutions are going to behave back in Cartesian space. Okay. So one of your homework problems for this chapter is to actually prove this, although it's not very difficult. Okay. Well, it's a good way to see if you understand what's in your notes or in the section itself. Okay. Okay. All right, so we have one section. Whoops. Left in this chapter.
But 0, 0, negative 1 is no longer a fixed one, but the solutions are still converging to it.
It's just because it's not a fixed point in spherical coordinates, but because all those different points in spherical map to the same point in Cartesian coordinates, it's still a fixed point. So if you were to try to take your original system, this system, with b equal 1 now, so it'd be extra terms, and try to find the fixed points of that directly, you would still find 0, 0, minus 1 as a fixed point. So what would happen, actually, if I go ahead and add this term on here, so it'd be minus y plus x, and then nothing changes down here. So let's suppose we set rho equal to 1. So that's gone, gone, gone. X and y are both 0. Gone, 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 gone. See, everything's gone. So 0, 0. Oh, that's interesting. Well, so actually any point of 0, 0 plus minus 1 is a fixed point of this system.
Yeah, in Cartesian coordinates.
In Cartesian coordinates.
So, but the solution is like just approaching 0, 0, -1 because phi is going to pi.
Right. Yeah, that's why it converges to that one and not the other one.
Right.
Yeah.
But in spherical, we see that there are no fixed points. So if we encounter such a problem, we have to, then go back again and see that if.
Yeah, because like suppose you were to visualize free space in a completely different way. Right. Like you would instead of having x, y, z axis, you'd have rho, theta, phi axis. Then you'd have this, instead of this one point that everything's converging to, you'd have this line that solutions are converging to.
Right. And that line has value phi equals negative 3 is going to pi, I think, right?
Yeah, so yeah, phi equals pi, rho equals 1, and then theta could be anything. So you draw that, you have this perfect straight line in the spherical space. But no one ever visualizes it that way because we'd like to visualize an x, y, z. It's kind of like in calculus, we talk about a polar rectangle. So r and theta combine to certain intervals, and then that is mapped to a circular sector in Cartesian coordinates. But it's called a polar rectangle. So, yeah. So because of a change of variables, you have this all kinds of deformation as you go from one system to another. Okay, so now 5.3, two theorems of importance, linearization theorem and the flow box theorem. So really the most general statements we can make about studying a nonlinear system by relating it to a linear system. Okay, so first I need to make some definitions. We'll also refresh your memory as to some definitions. Okay. What does it mean to be injective?
1-to-1.
Yeah, it's 1-to-1. Or an actual definition is all right, and then it's surjective. And the meaning of that is, okay, so this is, if f maps a certain domain to a certain range, that any y value in the range is f of some value in the domain. So nothing in the range is left out. And then what does it mean if it's bijective? Yeah. And it's bijective, what do we know about f?
It's a homomorphism?
No,
sorry, I'm thinking.
If you get group theory.
Well, that's true.
Isomorphism.
Whatever.
Yeah, homomorphism plus bijective is homomorphism.
Yeah.
But
Whatever.
those of you who have fond memories of homomorphisms from modern algebra, let me just make things a little confusing for you. So if f is bijective and continuous, and because it's bijective, it has an inverse. So if the inverse is also continuous, f is called a homeomorphism. So what a difference an E makes. Yeah, homeomorphism, not homomorphism from group theory. Okay. And I can add to the hierarchy one more time. If it is a homeomorphism and it's differentiable.
Hey, you already told us this one, didn't you?
Yeah, but I figure let's
I mean, I don't remember it, but
Exactly. That's why,
oh, big words.
yes, F is a diffeomorphism. Yeah, there's so many more, but these are all that we'll need. Okay, now, in particular, well, now we're going to focus on homeomorphisms. So word definition is we have two systems. X prime is big X, X. Y prime is big Y, a little y. We talked about differentiable equivalence. That means there's a diffeomorphism that relates these two. But here there's something a little weaker. They are topologically equivalent. If there exists a homeomorphism F that has these qualities, that if an integral curve alpha is an integral curve of x, it means if you have beta, which is f of alpha, is an integral curve of y. Okay. So it is an easy relationship between solutions of one system versus the other. And also important, it has to go the other way. So beta is the integral curve of y, means that alpha, which is f inverse of beta, is a integral curve of x. All right, so you can just use f and inverse to go back and forth between solutions of one system versus the other. Okay. So we'd like to be able to state conditions under which two systems are topologically equivalent or differentially equivalent. Mainly, the reason why I want to do that is, like, if your original system where big X is a nonlinear system, and your system with big Y is a related linear system, and of course you'd rather study the linear system because you can actually solve it. But you want to have some. You want to be able to believe that what you can learn about the linear system, Y prime is big Y, can actually tell you something about the solutions of the original nonlinear system. Otherwise, what's the point? Okay. Oh, so I need to drop this. Well, it seems like practically all my students have cracked phone screens. So why shouldn't I join the club, I guess?
Oh, I dropped it like 5 times while tutoring. Didn't even crack. So lucky.
Yeah, actually, I have dropped mine a zillion times even before I got a case for it, and it still didn't crack. Just got really lucky, I guess. Okay, now I need to recall another definition. Okay, so suppose that you have a point C that's a fixed point of your system. Okay, so C is hyperbolic. If the matrix A, which is the Jacobian matrix of X, evaluated at C, satisfies these conditions, that A has to be invertible, so determinant is non-zero, so there's no zero eigenvalues, and
Not zero.
yes, A is determinant A is non-zero, and
All eigenvalues are positive.
no, it has no purely imaginary eigenvalues. Another way of putting that is all eigenvalues have a non-zero real part. Okay. All right. So when you have fixed points, if they are hyperbolic fixed points, then we can say something about not differentiable equivalence, but topological equivalence. So this is what's called the linearization theorem. Okay, so linearization theorem says if a point C is a hyperbolic fixed point, of a system, this is like the original nonlinear system. So x prime is big X and little x is nonlinear. Then you can say that this system and this linear system, y prime is equal to ay, where A is the Jacobian matrix of big X at C. They are topologically equivalent. At least locally. So for X near C and for Y near the origin. So what that means is you can go ahead and solve the linear system, which you probably do exactly, and consider initial data near the origin, and then if you have if you can find an explicit homeomorphism between the two systems, then you can take your linear system solutions and map them using a homeomorphism and get solutions of the nonlinear systems. Now, maybe you can't necessarily find an explicit homeomorphism, but at least you can trust that the solutions have the same qualitative behavior. So whatever's happening around the origin for, if you were to do a phase portrait for this system, you can trust that you have similar behavior near C for this system. Now, how near is that valid? Hard to say. I know this is an existential result, really. It's not a constructive one. But at least it tells you when you can do this. But it's very important, this assumption that it's a hyperbolic fixed point, not just any old fixed point, for any of this to be valid. Okay. So I'll focus on that for a second. Okay. Now, to illustrate why, we look at this nonlinear system. So x prime is x squared, y prime is y. Okay. Now, what is a fixed point of this system? So what x and y values will...
0, 0.
Yeah, just the origin. So... Okay, so we'll look at the Jacobian. So big X prime of xy we take the derivatives of these right-hand sides with respect to x and y. So we get 2x, 0, 0, 1. So that's the Jacobian matrix. And then we plug in the fixed point. X and y both equal to 0. So we get 0, 0, 0, 1. So this is definitely a matrix whose determinant is 0. It's not invertible. So this is not a hyperbolic fixed point. Okay. Now, as far as how the solutions behave, okay, so the linear system that you would like this to be topologically equivalent to, you have x prime is equal to 0, and y prime is equal to y. So this is something that you can solve explicitly. So x is equal to an arbitrary constant, and y is equal to a constant times e to the t. So you can see how the solutions behave in this case. But the thing is, if you were to draw phase portraits of these two systems near the origin in both cases, you see that they're completely different. That there's the solutions of this system tell you absolutely nothing about the solutions of this system. So because it's not hyperbolic, linearization theorem doesn't apply. Okay. Now, let's see, another example to show why this assumption is important. And because if you look at the nonlinear system, you have x prime is equal to x squared. Well, that's going to be huge growth. Whereas in the linear system, you have x equal constant. So you can see right there why, for x away from a fixed point, even a slight little bit, you get nothing. There's completely different behavior. So I just want to confirm class analysis starts at 5 today?
Yeah.
Okay.
This is the time.
Yes, no, it's 4:45 crap.
Mm-hmm.
Okay. Okay.
So then we can't find it. And we can't find the solutions for that.
Right, yeah, the linear system tells you nothing about the nonlinear system. Okay.
Unless it's not hyperbolic.
Well, yeah. Now this one is not hyperbolic.
Yes,
Yeah.
so we can't.
Yeah. So you're completely out of line. Another example. Okay, so x prime is minus y minus x cubed minus x y squared. Y prime is x minus y cubed minus x squared y. Okay. So this system, you can see, also has a fixed point at 0, 0. There may be other ones, but this is what we'll focus on. Okay, so then you look at the Jacobian of this system. So you take the derivative with respect to take x prime and differentiate the right side with respect to x. And you get minus 3x squared minus y squared, and then with respect to y, you get minus 1 minus 2xy, and then this with respect to x, we get 1 minus 2xy. And then with respect to y, we get minus 3y squared minus x squared. Okay, and then you plug in x and y equals 0, 0. And you get 0, 0, minus 1, and 1. Okay.
Determinant non-zero.
Determinant is not 0. But what are the eigenvalues of this matrix?
0, 0.
No.
No?
No, there's not a diagonal. I mean, it is a diagonal, but
We looked the wrong way.
it's the
Yeah.
wrong way, so
Yeah.
you can't say it's the diagonal entries.
No. Way you can quickly tell what the eigenvalues are. The trace of a matrix, sum of the diagonal entries, that's 0. So that's the sum of the eigenvalues. So that tells you right away the eigenvalues are negatives of each other. The determinant is what?
1.
1. That is the product of the eigenvalues. Now the thing is, you have two numbers that are negatives of each other, and you multiply them, you get something positive. That seems a little bit odd. In fact, it seems a little bit imaginary.
Yes.
And that's exactly what happens in this case. So it turns out the eigenvalues are equal to plus or minus I. They are purely imaginary. So one of those good to know things, because this can come up in homework problems too, the matrix alpha, alpha, beta, minus beta has eigenvalues alpha plus or minus beta I. So the diagonal entries, which have to be the same for this to be valid, give you the real part, and then the betas give you imaginary parts. Okay, so you see that you're dealing with complex eigenvalues. Okay, so since the eigenvalues in this case are purely imaginary, that tells you that 0, 0 is not a hyperbolic fixed point, therefore the linearization theorem again does not apply. So you can go ahead and try solving the linear system and see how it behaves. So the behavior, if you look at the linear system, y prime is ay, where a is this matrix right here. If you were to work that out, solve the system, you actually get, so 0, 0 is a center. So it has a fixed point and then the solutions orbit around it. Because actually your solutions have a form of, they just give you concentric circles around the origin. Because x is equal to, x prime is minus y and y prime is equal to x. So that tells you x is equal to r cosine theta and y is r sine theta. So that's how you get concentric circles. Now, that's the linear system. But what about the nonlinear system? Zero, 0 is a fixed point that is called asymptotically stable. Now we saw that term a while ago. What that means is attracts nearby solutions. Nearby solutions. So solutions are not meant to stay in orbit at some safe distance from a fixed point. So it's not like a planet and these are moons orbiting around it. In the nonlinear system, the fixed point 0, 0 is like a black hole. So everything gets sucked into it. I can't say whether they get sucked in this fashion. They might go in a more direct way or maybe spiral around a little more. But the point is, they get sucked in. So again, completely different behavior for a linear versus nonlinear system, all because this fixed point is not hyperbolic. Okay. But if you have a fixed point that is hyperbolic, then yes, you can study the a linear system that comes from a Jacobian, and trust that the solutions, at least nearby the origin, look the same. All right. So we have 3 points, 3 types of points we can talk about. We have hyperbolic fixed points, which are covered by linearization theorem. We have non-hyperbolic fixed points, where the situation is hopeless. And then what about non-fixed points? Is there any way that you can say that that your nonlinear system at a non-fixed point is somehow equivalent to some linear system? And it turns out, surprisingly, not only is there an equivalence, but it's equivalent to a surprisingly simple linear system. And this is called the flow box theorem. So the flow box theorem says that if your vector field big X is C1, or it's, now by C1 I mean there's a common notation. It's continually differentiable. So the C means continuous, and the superscript means how many continuous derivatives it's known to have. So you often have like functions or set base function spaces being C1, C2, or even C infinity. And actually, I've rarely had occasion to use this notation in a class, though I could have. But it comes up in literature often enough, and you should know what it is. In fact, I wouldn't be surprised if at some point Dr. Ding uses it. Okay, let's suppose that C, little c, is not a fixed point. So big X of C is not 0. So I need to define a simple vector field, big Y, little y, is actually a constant vector field. It's E1, which you may recall is the first column of the identity matrix. So it's just a vector of 1 and all zeros after that. So it turns out these systems, x prime is big X little x, y prime is big Y of little y, which is this E1, are differentiably equivalent. For X in the neighborhood of C and Y in the neighborhood of the origin. So what that means is, if you think nonlinear system not at a fixed point, you might, so near this point C, who knows what behavior you're getting? Maybe you're getting solution curves that are behaving like that. So they're equivalent to this system where all the variables stay constant except for the first one. So what that means is the flow is just parallel to the x-axis. So this is what's happening with big X, the integral curves of that, and here the integral curves of big Y. These are just lines, horizontal lines that go on forever, all parallel to the x-axis. So this is only happening near these points, C in this case, and the origin in this case. So if you zoom on this enough, the behavior is always something like this. Maybe it's more curvilinear, or maybe it's doing something like that. But the point is, you can basically take these curves and straighten them out. So in fact, you can reduce the behavior of a nonlinear system to really uninteresting behavior, simple behavior. Okay. And really all it takes is, well, as when I was saying a differential equivalent, that means that there's a diffeomorphism that relates this system to this one. Now, whether you can construct that is another matter. Maybe you can only construct it approximately by like using numerical solutions. How much time do I have?
5 minutes.
Okay.
So why do you get parallel lines? Is it constant, like in terms of something?
It's because of this choice of vector field, where so in the xy plane, for instance, only x is changing, y is constant. I could have chosen something different, like if I chose 0, 1, then it'd be going up. But the point is, you can make it as simple as you want.
Right.
And I figure you might as well go for the simplest vector field that you can make it equivalent to. Because what all this is saying is, if you don't have a fixed point, then what do you have? Flow in some direction. And is close enough to the fixed point, you can have different integral curves going in different directions technically, but the directions are similar enough to one another, then you can just take them and straighten them out and get parallel lines. So you're not, as long as you keep in mind that this is local, you're not going to have like wildly different behavior so close to the fixed point that you can't straighten it out. Okay. I actually would like to talk about the proof, or at least the main idea of a proof of a Flowbox theorem, because that's a very interesting linear algebra exercise, but not in 3 or 4 minutes. So I will use that to start off Wednesday. So the 4 of you anyway, I guess the frontmost 4, good luck on linear analysis test take 2.
Oh, is that today?
Yeah.